Welcome to the 10th presentation in the 6th webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the 10th webinar of our 6th series, which will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the 6th series will be distributed through the IAS mailing list, Twitter feed, and LinkedIn page. Today's webinar will be given by Dr. Maria Papathanasiou at Imperial College London in the United Kingdom. I am Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by Nicole Ferrou at ETH Zurich in Switzerland. We're required to remind attendees and future viewers that the views expressed by the speaker, host, and other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsots for future updates regarding IAS events, webinars, and information about scientific meetings. We also have an IAS LinkedIn page, which can be found by searching for the International Adsorption Society or the link on the screen. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to Nicole Ferrou, who will moderate the YouTube Q&A.
It is my pleasure to welcome Dr. Maria Papathanasiou to today's webinar session. Dr. Maria Papathanasiou is an associate professor at the Department of Chemical Engineering at Imperial College London. She holds a PhD degree in Process Systems Engineering from the Department of Chemical Engineering at Imperial College London and a diploma from the School of Chemical Engineering at the National Technical University of Athens. She conducted her diploma thesis in food process engineering at the Technical University of Berlin. I remind you that during the webinar, you can ask questions to the speaker by submitting them as comments on the YouTube live stream, and the questions will be answered at the end of the presentation. With that, I welcome Dr. Maria Papathanasiou again and pass over the presentation to her.
Thank you for the kind introduction, Nicole. I will just now share my screen. Hopefully that will go very smoothly. I'm hoping you can all see my slides now.
Yes, we can hear and see you very well.
Thank you. So thank you, first of all, for the kind invitation. It's a great pleasure for me to present to IAS and the webinar series. As you saw, I come from a process systems engineering background, and I'm really looking forward to some idea and research exchange through this talk. Before I kick off and I show you a little bit of what we have done and how we think process systems engineering can be useful in this setting, these are the people who I would like to thank. So I'll start with the acknowledgements, actually extending my thanks to my group that are the people behind everything that you will see, particularly Fotini, who is standing here in the orange top and who is actually soon to be graduating from her degree. Before I go into the nitty-gritty details of the modeling that we have been doing in ion exchange chromatography, I think for you to understand and sort of appreciate the reason why we ventured into machine learning helping us modeling these kind of systems, it's worth for me spending a little bit of time in explaining to you the motivation. So a big chunk, I would say, of the activities in my lab are focusing on the curious case, as I like to call it, of biopharma manufacturing. So in biopharma, as you may already know, we have started from non-specialized drugs known as small molecules. And as years progress and the clinical understanding is also increasing, we move on to even what we know today as personalized medicine. So these are usually cell-based therapies that entail a lot of variability, but from a clinical perspective, they target an individual patient. So they have extremely promising clinical power or approach. But at the same time, this means that from an engineering perspective, the complexity of the system that we're manufacturing these drugs is increasing exponentially. Now, as I said, most of the advanced therapeutics are cell-based, and so that means that we usually have a bioreactor where we feed those cells with nutrients, and this bioreactor is then giving us the product as well with impurities. This, of course, system on its own has multiple levels of complexity with respect to scale. So there are labs out there looking at the cell culture level, the individual level, the population level. But what interests my lab in the area of separation modeling is how complex these systems are and how expensive, right? So for us to gain data, even at the purification stage, is very, very hard because it's very slow and very expensive to even produce these therapeutics upstream. In biopharma manufacturing, way the pharma works is quite sort of regulated, tightly regulated, right? So processes are very well standardized. Nonetheless, we're talking about living cells that are producing the product of interest, which means that in the way each of us does not digest the food the same way every day, those cells do not produce the same level of product or the same level of impurities every day. So there is a standardized window of operation, but still we should expect some variability in the process to occur. And this variability that is created at the upstream level is then impacting the purification trend. And this is why downstream purification in biopharma manufacturing needs to be tightly monitored, but also extremely well understood in order to be agile to kind of undertake this variability that comes from upstream. And in that, it's no news that process modeling can actually help us understand all of these dynamics and a priori assess different setups, different unit operation setups and optimization scenarios for the process operation that might yield an improved process. But when we develop models, there are many questions for us to ask ourselves. The first is the purpose, right? What do we want it to do? Do we want this model to sit just for simulation open loop? Do we want it for optimization? Do we want it for control, right? And every bit of this one, and I think the list is a lot more granular than what I'm showing on this slide, has a different model architecture that may be suitable. The second, which is particularly a big challenge for this industry, is data. In the case of biopharma manufacturing, data is almost literally gold. It's, as I said, it's very expensive, it's slow to obtain. And so also industrial efforts are focusing in generating a lot of data around conditions that work, right? So that we can have some certainty that our processes are standardized, which from a modeling perspective is not always ideal. In order for us to create models that capture a variety of conditions, we need data in this variety of conditions, which is not always the case. And finally, analytics, this is particularly relevant when we talk about online optimization or control. So we don't necessarily have all the online sensors that we would have liked to get feedback information on the fly. The last part, which we sometimes in process systems engineering tend to forget, is the user. So we create model for someone to use it, right? So that user is not necessarily a super expert in modeling techniques and whatnot. They may be experimentalists who would like to use the model for experimental design or for quick condition screening, which does not necessarily mean they have knowledge in creating and using a high fidelity process model. So As you know, there are at least 3 major categories of modeling: white, gray, and black box type of models, or in other words, mechanistic models, hybrid models, and data-driven models. And each of them has pros and cons. Starting with the mechanistic model, undoubtedly, this is one, let's say, of the categories that has, or the only category that provides the most information about the system, right? So if we want to gain mechanistic understanding and actually get predictions that are of high accuracy, then mechanistic model is indeed the way to go. Nonetheless, particularly in the area of chromatographic separation systems, these are often models that are slow to converge, slow to simulate, particularly when they're integrated in optimization policies and control formulations, simply because they rely on partial differential equations and they include highly nonlinear terms. So from a simulation perspective, they're quite challenging to deal with. The other end is looking at black box or data-driven models that essentially contain no mechanistic understanding. They're based on data and data quantity, particularly that could be a challenge at early stage experimentation, as I mentioned. But on the downside, if you like, they require often large data sets and they provide almost no information on the system specific, unless we venture into explainable AI, which is not the focus of this talk today. In the middle lies a category called hybrid modeling, where essentially tries to combine the best of both worlds, right? So we try to maintain a percentage of mechanistic understanding from the white box approaches while combining it with black box techniques or formulations. And that is actually trying to reduce the computational complexity or perhaps help us describe phenomena that we're not necessarily certain how to explain mechanistically. But of course, there also lie challenges in the development and execution of hybrid models. One of those could be uncertainty propagation. And now I would like to spend some time focusing on today's use case. So as I told you, in biopharma manufacturing, we have the upstream. This is where we produce the drug. And then we have a quite populated downstream operating train. Today, we're going to focus on polishing, in fact, ion exchange chromatography. And to look a little bit deeper from the application side and its challenges, as I mentioned many times by now, we have very limited data availability, but also lack of analytics. At the same time, as I told you before, we've got some level of feed variability to expect. And so the unit operation needs to be designed and optimized in a way that can handle that. At the same time, we've got multiple variables we can play around with based on the system specifics, but also we need to be aware that interactions between components are there, right? So we need to start understanding how one affects the other. From a modeling perspective, these models often are comprise partial differential and algebraic equations. They're quite big and nonlinear. So if we want to use them for optimization and control, they present certain challenges. And finally, when it comes to monitoring, of course, we need to consider what are the time limitations or requirements for us in order to provide solutions that can work within the timeline that we have for the process. The unit operation of focus for the work we have been doing is the multi-column countercurrent solvent gradient purification process, the MCSGP, which in this case we're looking at twin column setup. This is basically an innovation by the Morbidelli group. It has seen multiple versions of it. We're looking at the twin column one. And fun fact is actually where the unit operation I used for the application of my own PhD back in the day. It's an ion exchange chromatographic system that operates continuously. So as you see here, we have the I phases where the columns are interconnected and the impure fractions are recycled. And we have the B phases where the columns operate in batch, where usually is when we collect the product of interest, which is denoted as P here. And we feed fresh feed from the from the previous steps into the column, right? Ideally, we want our process to operate under cyclic steady state, so we have some stability in the way we collect the product. And another point to look at is how narrow is the collection window in this process. So we're actually collecting the product that we're after over 90% purity in a very short fraction of all of these cycle, right? So we need to get the story straight almost from the beginning. Another thing to mention here is that optimizing not only the way this performs, but also the collection window is of high importance, because in biopharma, yield is, of course, a performance indicator, but if we collect products that do not meet the purity constraint, but we are actually very productive, this means nothing, because if we don't hit the purity specification, then the product is simply going to the bin. Let's dive a little bit more into the model. I'm not going to spend a long time here explaining to you the equations. I think you probably know them better than myself. But essentially, it's a quite standard model, lamp kinetics. Here, looking at liquid and solid phase concentrations, the isotherms, and a different set of equations here, looking at the boundary conditions, the Henry constants, and whatnot. What I want to focus on is the metrics of this model, that after discretizing the space, so the column length, using 50 collocation points, we end up with over 3,000 variables and 4,000 equations for this model. So it's quite considerable in size and quite nonlinear, as you can observe from the equations. So in ion exchange chromatography, as I showed you, for particularly this case study, there are multiple challenges we need to assess, right? So, and these are all unit operation specific. How do I operate my unit? When do I reach cyclic state, etc. Many of these, though, decisions are also product specific. So very oftentimes, we need to transfer also from one product to the next. And in this case, high fidelity process models would need to be reparameterized. And then this is where we hit perhaps either the expertise challenge or the time we have at our disposal challenge, and so on. So, and the third thing that we were thinking when sort of outlined this project was, how do we monitor these columns, right? How do we develop controllers that can optimize and these columns and sort of hedge against the variability of the feed? Now, this is when we came up with the idea to assess what machine learning can do for us in order to have perhaps models that could be transferable just based on a few data points. And of course, the million-dollar question, if you ask me, can we develop black box models just from data? And what is this number of data points that we need in order to develop these black box models, and how or where all do these modeling techniques fit? So the first thing for us to do that was to follow a formal model analysis and look at the problem formulation and understand where does the complexity from a mathematical perspective come from. And this comes from the discretization of the space in this case, right? We also would like to predict at times directly at cyclic steady state to understand how our optimized process might work. And so with that in mind, what we did, the next step was to sort of develop the architecture for the machine learning tools that I will show you in a second. And the first is data generation. In this case, of course, we have the luxury, if you like, to have a validated process model, high fidelity process model that we used as the data generation system. And so we had to define the inputs and the outputs and train the neural net. And finally, eventually test these models to understand what's their usefulness, right? So we were quite critical in posing the research question. We said, okay, first of all, let's see whether we can do it with machine learning, but also why do it with machine learning, right? So if you have a validated process model, is there any reason for which you would go towards a more black box route? So the first approach was to develop a full black box model. So in this case, there will be no mechanistic component in this architecture. And so for the input layers, we looked at concentration of the feed, which is the measured disturbance, the flow rates, which we can play around, and the concentration of the modifier that is also a manipulated variable. We use a quite, or try to use a quite small architecture, as you see, up to 4 hidden layers and up to 256 neurons. And we operated, as I said, oh, I'm sorry, there is an overlap of the slide. We operated the high fidelity process model as the unit operation in silico, as the digital shadow of the unit, and we generated data to be able to collect our output. So we changed, or we excited the operating conditions of the feed, the flow rates, and the modifier concentration within the fidelity region of the original model. And then at cyclic steady state, we collected dynamic inputs for the inlet of the modifier and the outlet of solid phase equilibria. So the first thing we tried to do is assess different activation functions for these models. So there are different ways you can actually tune a neural network, and we wanted to see how well those might perform. So the other question we looked at the same time is how low can we go with the sample size of the data we use for the training of the models. So whenever you see here a sample size of 400, for example, this means collecting over 400 cycles. And so you see here that we don't necessarily see any massive change with respect to the performance of the different activation functions, but the most important takeaway is that for this particular scenario, we have good agreement between the high fidelity process model and the different black box approaches. Very importantly, what was very interesting for us to see is that the elution window, which is the pink band you see on all these graphs, was very accurately captured. And this is very important for us to know that we can predict what takes place during the collection window of the product. And then we started going down with a sample size. This is 200 samples, 100 samples, and 50 samples when we started seeing some sort of significant, I would say, mismatch between the black box approach and the high fidelity process model. Nonetheless, the collection window of the product performed quite accurately across the board. So this is a first, if you like, quantitative approach. Here is with 25 cycles, for example, in order to understand, first of all, the impact of the data set size and the activation function in the performance of a full black box for such a complex system. So the next step was, okay, we have now this black box model. Since we have mechanistic understanding of the process, is there any way we can retain that mechanistic understanding and only black box the things that complicate our live computation, right? So now we ventured into a hybrid formulation. So if I go back to the process model over here, the complexity, as I mentioned to you before, comes primarily from the partial differentials that I have in my system, right? So what I'm going to do in the next few slides, I'm going to show you how we approximated this part of the model through a black box approach to eliminate the spatial discretization and try to reduce the computational complexity of this model, because we want to see eventually if we can improve computational time using such a model in an optimization, online optimization approach. The other thing we kept in mind was transferability of this model. So in this case, we made sure that if we ever were to transfer this model across a different product, we are relying on experimentally measurable entities and variables. So the hybrid model architecture considers experimentally defined parameters. In this case, experiment is our in silico experiment, our in silico process model, and disturbances or user-defined inputs that are the feed, the flow rate, again, and the modifier concentration. The hybrid formulation, as I said, is maintaining part of the model explicitly, right? And it's approximated the partial differential equations in this step. Very importantly, as you know, the systems sort of have a lag, right? So once you feed something at the column inlet, it takes X number of minutes to reach the column outlet. For this reason, at each time step, we collected both at time t plus time T plus dt, where dt was actually the time the component needed to reach the column outlet. So through this pseudo-dynamic input-output set, we try to inform the black box part of the model that there is an inherent delay in the system. So you don't feed at time 0 and you actually collect at time 0. So this hybrid formulation is actually looking at the column outlet, solid phase equilibria and time, and is actually predicting liquid phase concentrations, and eventually from these we can calculate purity and yield. So now we have at our disposal the original mechanistic model, the black box, and the hybrid formulation. And so we tried to, first of all, oh, I'm sorry, I just forgot to mention that, which is something very important I forgot to mention, in fact, how we tune these black box models. Both in the case of the data-driven and the hybrid formulation, we had to do some sort of formal Bayesian optimization for the tuning of the parameters. The reason for this is because essentially, because of the elution profiles, the collection window, or the time that these concentrations are not 0, right, is approximately 6% of the entire data set. So in the beginning, the black box formulations were trying to match the majority of the data points were actually flatlining to 0. So we had to employ formal hyperparameter tuning in order for those black box entities to understand that the data set was highly imbalanced. So how do we assess the performance, right? So we wanted to look at elution profile, simulation time, and interpolation and extrapolation capabilities of those models as compared to the mechanistic counterpart, right? So the first objective to use any kind of model would be to improve process efficiency. Now, excluding, of course, gaining mechanistic understanding, right? So if we want to improve process efficiency and do some sort of model-based optimization or process optimization, we would use a model. And this is exactly what we sort of did here. You see here, first of all, simulations in open loop of the 3 models, first in the nominal conditions, then interpolating and then extrapolating within the fidelity region of the original mechanistic model. And you see quite a good comparison between the mechanistic component and the 2 counterparts, the black box and the data-driven. We, of course, have discrepancies, right? But at the same time, for the majority of these, the elution window and the product concentration during that is quite well captured. Most of the time, also, when we have discrepancies during elution of the product, we actually have an underestimation of the purity component rather than an overestimation, which is where we would like to be ideally in case of not perfect match. So we would much rather underestimate the purity predicted than overestimate it, which means we would actually suboptimally optimize the process for a product that does not meet the specs. And now if we use these models for optimization, if our objective is to maximize the yield of the process under a strict purity constraint over 98%, we are looking at optimizing process flow rates using nominal conditions of our feed stream. And then the next step would be to simulate the outputs with the mechanistic model and use them to understand how well it works. So what we do here is that we set and define the same optimization problem across the board for all 3 models. And then for the black box and hybrid component, we take the optimal input, if you like, set, and we run it through the mechanistic model to see how well actually we can capture that. So what you see here at first is actually a good agreement, right, across the 3 models. So as you see, they achieve pretty much comparable yield. And the flow rates as well that are predicted through this optimization are very close to one another. So we have some certainty that the optimization we perform using the black box and the hybrid formulation can yield trustworthy results, right, when used. The advantage here of using these two types of models to run the offline optimization is purely computational expense, right? So they're a lot faster, orders of magnitude faster than doing that with a mechanistic model. We also tested the optimization under two different constraints. So here we assume that we've got a time constraint of 60 minutes. So we perform what's known as cycle-to-cycle optimization. Our cycle is roughly 60 minutes. And so we assume that the optimizer can only fix one cycle ahead. Also here we see comparable approaches. Of course, you see here that the hybrid formulation is quite over-predicting in this case, and we believe that this could be attributed to some sort of error propagation. Now, think about a model that has a black box component, but also has a nonlinear component, right? So the phase switching and whatnot, and this complex schedule do not lend themselves very much to handling the error extremely well. In this case, this also work under investigation on our end, but this is the understanding that we have. What actually was striking for us is when we imposed a minute-by-minute optimization policy. Now, in this case, we imposed to the optimizer a 1 minute constraint. So it had to optimize every minute for the next minute. And if you notice, there is actually an empty number, empty values for the mechanistic component. This is simply computationally not possible to achieve with using the full mechanistic model. So if we were going towards a more online optimization approach where we had to use an in silico platform to optimize and then tune our process or unit operation accordingly, we would not be able to operate that fast using a full mechanistic model formulation. So here, the computational advantage is actually very highlighted. And before I jump to sort of the second case study, which is more on control, just a few remarks here. We developed and assessed both a hybrid and a data-driven avenue to predict the dynamic elution profiles at cyclic steady state. And we actually noticed a reduced computational cost by a striking 97 and 99% respectively, 97 for the hybrid and 99 for the black box. The models were implemented within a Bayesian optimization framework to optimize those flow rates. And as you saw, they compared quite favorably under multiple scenarios that we looked at, which is both interpolating and extrapolating. Now, all of this work has been disseminated publicly. There are 2 journal publications. You can see the references for those at the bottom of the slide. And it's something now, along those lines here, we're looking to see how we can utilize other techniques, for example, transfer learning, to transfer those models from one product to the next. So now I'm going to switch gears a little bit and talk about process monitoring. Now assume a scenario that we would like this column to have a controller running on top of it, right? So it can actually move towards a more automated way of operation. Now, for this reason here, we looked at reinforcement learning. Just as a fun fact myself, I did my PhD on model predictive control for this exact unit, NPID. And so we looked at machine learning here, again, first of all, for the computational advantages that this may offer, but also because it's not strictly acquiring a model-wide works, right? So we have some flexibility because we're learning patterns to potentially increase transferability of this scheme. So what happens here is that you have your environment, which in this case is the 2 columns. Just to explain that here we assume that we can control the flow rate of one and that we fix the flow rate of the column operating always at maximum. So the column on the left, we already know that operates at maximum flow rate. So we fix that and we control the flow rate of the column on the right-hand side. And so the controller has exactly this task. When we were looking at how to design the reward function, so here is basically the controller's objective, right? And the controller is rewarded at every phase. How does this happen? There are sort of weights for impurities, product, and the product, so for weak and strong impurities and the product, but also there is a penalty that is linked to the phase duration, right? So we don't want cycles to last and phases to last endlessly. So we penalize the controller in case it does that. In this case, both the phase duration and the flow rate are actually variable and at the discretion of the controller to decide the value for those. So what we did in the beginning is that we actually simulated the process model for 100 episodes from process startup. So in this case, we're also considering startup. And each episode comprises 5 process cycles. So we used 500 cycles for the training of this control. So the first thing we assessed was the performance of the process from the get-go, from startup. So what you see here is the concentration of the species here across the cycles and the flow rate. So you see that we reach cyclic steady state relatively quickly, so cycle 5 give or take with some sort of tolerance. And you see here as an indication the column flow rate and the outlets, how they propagate. Under cyclic steady state, which is quite an important indication, we looked at the concentration of the species at the outlet, but also we compared the nominal collection window, which is the pink one, and the light blue collection window, which is what the controller suggests. So the collection window is actually shifted towards the front. And as you can see, the purity constraint is met, but the reinforcement, the controller achieves 1% less yield, but the recovery is actually higher. So that has to do also with the flow rate that the controller is imposing. Essentially, here we're looking at the problem from a different angle. We look at the threshold of the purity. So you see that the performance is quite favorable, right? Where compared to the original system that had been optimized. Some learnings we can actually gain here is that the controller is changing the phase with respect to the purity threshold, right? So you see that the higher the purity, the controller decides to actually increase the I2 phase, which is the recycle phase of the impure fractions, to increase by 2 minutes. So there is some sort of, if you like, certainty that the 500 cycles fed into the reinforcement learning controller have actually propagated or transferred, if you like, understandings of the system and the dynamics in there. As I mentioned to you before in the early slides of this presentation, these systems suffer, if you like, from feed variability. So we wanted to assess how the controller can actually perform if we were to increase or decrease the concentration of the product by 20% and same for the impurities. So we designed a favorable scenario where the concentration of the product is 20% higher than what we usually get at the nominal conditions, but the impurities are actually 20% lower. So we assume here a purer feed that the controller has to handle. Whereas on the right-hand side of the slide, we assume a pessimistic scenario where impurities are increased by 20% and the product concentration is decreased by 20%. So you see that there are significant, basically, changes in the way, essentially, in the collection window, first of all, but also naturally at the scenario of the favorable conditions, which is the dotted line, we managed to recover a lot more product. And this is normal because we also feed more product. We also see that the purity threshold is met in both occasions. So in this case, we also then wanted to assess how the controller might actually operate under flow rate disturbances. So let's assume that the pumps don't always go as we expect them, so we actually have some disturbances during the phases, right? What happens then? So we run the controller in that setting, and what we actually see is that we pretty much, again, achieve the separation, perhaps less favorably than before, but the controller still manages, even though cyclic steady state is massively disturbed, to bring the system to sort of an operation where the product can still be collected. The last sort of, if you like, scenario we assessed for the controller is that of measurement noise. So we assume here that there is absorbance noise in the UV signals we receive. This is just for illustration purposes, but we assumed up to 5% noise on the pulled outlet concentration. And so in this case, we used the model, the mechanistic formulation, as an auxiliary tool to distribute the concentration. So you see here that the controller performs quite well. Also in this occasion, again, in this case, if we had to prioritize, perhaps cyclic steady state would not be our priority, would actually be rejecting the noise we receive from the measurements and still managing to collect the product on the right time with the right purity. To conclude, the reinforcement learning controller for this twin column system has actually shown some sort of, if you like, agility to perform under different conditions, under disturbances that include perhaps feed variability, but also noise in the measurements that we receive, but also very importantly, it managed to help us optimize the startup and reach cyclic steady state perhaps a little bit faster than the open loop simulation. We also looked at the purity constraints, and it was ensured across all of these scenarios, which is the ultimate goal in the case of the biopharma separation we're looking at here. Now, I've been talking for so long about different modeling techniques and mostly about the advent of machine learning in the area of separations. For transparency, I started my journey in process systems engineering being a huge advocate, and still am, of high fidelity process modeling. I believe this is, again, the way for us to gain mechanistic understanding. But where I see perhaps such type of tools fitting in is under an umbrella where all these tools can actually be helpful. So the way we envisage tools like the ones I presented to you here being integrated is at different parts of the process development, operation, and then monitoring. To give you a quick example, the black box technique that I showed you very early on in the beginning perhaps would be suitable if somebody wants to very quickly assess different processing conditions and the performance of the column under those, without necessarily this person as a user having a massive or very deep expertise in mechanistic modeling. The hybrid formulation would perhaps lend itself to an easier, if you like, transferability to different conditions and different, particularly different products that can be separated, as it entails in its formulation and in its architecture, things that we can actually measure in the lab. And finally, the reinforcement learning control scheme that I showed you, it has quite significant, if you like, capabilities of monitoring such systems, even working in tandem with an in silico model formulation when the signals are not available, but the speed under which it can perform and the ability it has to learn patterns is quite favorable for systems like this one, that variability can be quite high. And so we saw through this example that I showed you that it has the capability to, first of all, ensure the ultimate goal, which is the purity constraint. And with that, I'll stop here, and I'm very happy to take any questions you may have.
Thank you, Maria, for this very interesting presentation. First question that we have is, how much experimental data is required to get an approximately good prediction? So, and how long would it maybe take to get this experimental data? And does that still yield a speed up in terms of overall process simulation?
That's an excellent question. This is actually the question that motivated us to study the impact of the data set size in the first place. I would say that up down to 50 process cycles, we managed to actually have a good black box model with reliable predictions. And I would say that through a work that we've done in a different space, where actually we use transfer learning to adapt black box formulations to new conditions that they haven't seen before, we have managed to do this with actually as low as 9 different runs. So take it with a pinch of salt, but I think if we also combine this with transfer learning, we can get pretty low, in which case, yes, indeed, the computational expense is still a significant gain.
And as a follow-up question to that, how well sampled do these experiments need to be?
How well sampled? I assume that would be referring to the frequency. So I'll answer based on that, but please feel free to clarify if this is not what you mean. Then I would say that typically all these units have UV sensors on them, so the frequency that UV signal is collected would be enough.
Okay, perfect. Then another clarification question is that you talked about transferring your models across products. Is the framework you propose adsorbent specific, or agnostic?
So in this case, it's pretty agnostic as long as the kinetics are similar, I would say.
Okay, perfect. And you showed elution profiles, and how does predicting the process performance metrics from the elution profiles rather than predicting them from the inlet or operating conditions, how does it affect the accuracy of the predictions of performance metrics?
So in this case, performance metrics of interest have been purity and yield, which are actually calculated by the outlet concentrations at the or during the collection or the elution of the product. And this is why we focus on elution profiles. We really want to make sure that during this narrow band of product collection, we have accurate prediction of these concentrations. In other occasions where perhaps the metrics are different, this can change, and so I would assume that the output set would also be adapted.
Perfect. We have another question coming from David Danacci, who is asking, how does the RL approach compare to something like MPC-based black box models?
Yeah, so that's a good point. Thank you, David. MPC is my own PhD on this system. So if you're very curious, you can also look at these publications, and I can actually tell you how it compares. So model predictive control is model-based. This means you have a model. Typically, nonlinear MPC is quite complex, so we would go perhaps for a linear formulation of this model, which means that the partial differential equation model I showed you would need to be linearized, either linearized or approximated through what we call a linear state space, in which case you have lost a lot of information on the nonlinear behavior. I think they can both work equally well. Perhaps one point of the reinforcement learning controller that is a plus would be the fact that it learns patterns rather than relying to a model, so it can perhaps be adapted faster to things that look like what it has been trained on, but are not exactly like this. Also, from a user perspective, it can perhaps require a lot less specialization in the specific control expertise and the design of the problem. But definitely MPC has its own advantages as you carry forward, if you like, some mechanistic understanding, some sort of certainty that the controller outputs can be fed back and assessed in a closed loop with your digital twin. So they would perhaps serve a different purpose given also what modeling assets and what types of sensors you have available.
Perfect. I think that was a very clear answer. Maybe let's go a bit more general with the questions. You mentioned in the beginning that uncertainty can be an issue. So how do you handle uncertainty propagation in your hybrid models, especially with limited online analytics?
Yeah, that's an excellent question. In fact, here I talked about uncertainty propagation from its mathematical perspective. So first of all, we have guarantees that the mass balances are actually closed, because that can happen from a solver perspective. With respect to measurement uncertainty, I think what we have been trying to do is actually train the models within a certain range of conditions. And so we have certainty that the model can predict accurately within this range. Anything outside this range, so true extrapolation with machine learning, I think is a very dangerous task. So I would not recommend that. So I think this is what we have actually looked so far.
Okay, great. Then as a last question, we're going even more general. What advice could you give someone attempting to build a machine learning framework like this, maybe for a different application?
Oh, yeah. Okay. So that's an interesting one. So first of all, I think what we asked ourselves perhaps halfway through the project is, why do you need it? I think it was a reviewer in one of our conference papers who actually asked us, why do you need a neural network if you have the high fidelity process model in place? I think that's a fair game question. And so that made us think of how different models can fit under a suite of tools, right, for the approach. So first of all, what's the purpose of this model? And the second would indeed be what I think was, the first question you asked me, on data size and its availability, right? Whether that's even possible to do it. So I think these two primary things, I would go and tackle them from the get-go.
Perfect. Thank you very much for your answers and your presentation. And I give it back to Nick for the closing of this.
Thank you.
All right, thank you, Dr. Maria Papathanasiou, for your presentation, From White to Black Box Approaches in Chromatography Modeling. We also thank all of our attendees for joining this webinar and hope it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili. The hope is that the work discussed here today will be a useful resource for the absorption science community in the future. The next confirmed IAS webinar will be given by Dr. Mauro Luberti on November 12th at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed, LinkedIn page, and through the IAS mailing list. With that, we thank you for joining us and hope that you will join us again soon.